Okay, so in this video, like we've done in previous videos with different types of equations, we're modeling real-world stuff and seeing how these types of equations can be solved to solve word problems, okay? Because it's important to know how to solve word problems. So quadratics are used to model many things such as the height of a falling object. For instance, when an object's dropped, its speed will continuously increase and its height above the ground is going to decrease at a faster and faster rate. The height h in feet of the object t seconds after it's dropped is modeled by this equation where h of o is the initial height. Now, a couple things about this model. It assumes that the force of air resistance is negligible. That means we're not going to take into the account the wind pushing back up on whatever we drop. And this model also only works on the Earth because other planets have different gravities. So this formula has been tailor-made for our gravity here on Earth. If you go to, say, Mars or the Moon or something like that, a Moon colony or Mars colony, this formula is not going to work anymore. You're going to have to use a different formula. So just keep that in mind. All right, so in this example 27, we have a stuntman who's working on the set of a movie, and he's going to fall out of a window 100 feet above the ground. For the stuntman's safety, we have an air cushion that's 26 feet by 30 feet long and 9 feet high is positioned on the ground below the window. For how many seconds would a stuntman fall before he reaches the cushion? So let's work on part A first. Very first thing we want to do is to label what we're given in the problem. So here, a stuntman's working on a set, he's spotted a window 100 feet above the ground. So that's his original height, so h of 0. Now, we got to be careful here. 26 feet by 30 feet by 9 feet high. We only care about his vertical position. So 9 feet is what we need. That's his final height. So regular h. 26 and 30 are a horizontal unit, so I don't need those. If it helps you, draw a picture. Our stuntman's on top of the building. You can see I'm a great artist, and we have a little air cushion at the bottom. This air cushion is 9 feet tall, and essentially, he's dropping. He's 100 feet tall right here. And he's going to drop all the way down. So we want to figure out how many seconds will he fall before he reaches that air cushion. Okay, so just keep that in mind. All right, so now that we have our information, we're going to plug into our formula. So we're doing A in green. So our final, we're using this formula right here. So our final height is 9 equals negative 16t squared plus our original height, which was 100. Okay? Well, we could, of course, solve this by hand, but we have the technology, so let's practice solving by graphing. Left side is always y1. Right side is always y2. And as always, our calculator only understands x's and y's, so we're going to pretend that t, or time, is going to be an x temporarily. All right, so y equals, clear it out. So 9 and negative 16x squared plus 100. Graph, and every time we do a new picture, let's hit zoom 6. Okay, so now obviously I'm seeing some kinds of intersection, 2 points of intersection. So let's go ahead and find what those 2 points of intersection are. Point of intersection here on the left, point of intersection here on the right. So second calc, option 5. First curve enter, second curve just hit enter, and then guess. We're going to move our cursor until we think it's in position, which I'm pretty confident it is. And I'm told that my point of intersection on the left is x equals, or in this case t equals negative 2.38. Now this is time, so that's seconds. Let's find the other point of intersection over here on the right. So repeat the process. Second calc, option 5 for intersection. First curve, just hit enter. Second curve, just hit enter. And then guess. I'm going to move over to the right until my cursor is in position. And that's probably pretty good there. And I get positive 2.38 for my time. All right, now I have 2 solutions. However, based on the problem, we're talking about real-world stuff. We have a positive time and negative time. Well, you've got to ask yourself, does it make sense to talk about negative time? And hopefully you agree with me that negative time makes no sense at all. We don't have a time machine, okay? He's not jumping through some space portal that's going to take him back in time in 2 seconds. Okay, that would cause a paradox, and he would just keep falling over and over and over. Doesn't make sense. So this is gone. So based on this process, we're talking about a real-world situation. Time is always positive. Okay, so this is our only answer. So it's going to take him about 2.38 seconds to jump from the top of the building all the way down before he makes first contact with that air cushion. All right, so now in part B, let's do that in red. We said that a movie camera is filming this whole jump at a speed of 24 frames per second. Frames per second, that's important. And it records the stuntman's fall. We want to know how many frames of film show the stuntman's falling. So what I want to do is take my answer in part A and multiply it by 24. Because it's frames per second. The keyword per means divide. Now, seconds and seconds are going to cancel out. And what's left is, for my unit, is just frames. So when I do this, I'm going to use my calculator. Go back to my main screen. 2.38 times 24 tells me there's approximately 57 frames of film are going to be used. So we can see how these two problems build off of each other. We first found the time, and then we first found out how many frames of film are being used to record that fall for the movie. And this is just a quick example of how quadratics can be used to model real-world data. Quadratics are used all the time. Again, you take a physics class, you're going to see them over and over again. Hopefully this video helps a little bit.